Okay, in this video we're going to continue talking about projectile motion. Specifically, we're going to be interested in deriving what's called the range formula. And maybe I'll just get right into it right here. So what we're wanting to look at now is the range of a projectile. So I'm going to set up our x and y coordinates here. So this will be x, this will be y. And we can imagine that some projectile is launched from our origin, and it follows a path something like this, right? So this path is going to be its trajectory, and this is going to be a parabolic path. Okay, so I'm going to set up some coordinates here. This is going to be our initial x coordinate and y coordinate, and these are simply going to be 0 each, right? And then over here at some x final and y final, we're going to have our x coordinate equal to whatever it happens to be. Oops. And our y coordinate is going to be 0, right? Because we're ending up back at y equals 0 here. So what we're interested in is what this distance in here is going to be, and we're going to generate a formula for that. We're going to call this the range, and it's going to be signified by this capital R. And we're going to be wanting to calculate what the range of a projectile that is launched and lands at the same height here, right? So we have to remember that for this range formula, that the range formula is going to apply only when y naught equals our final y equals 0 in our coordinate system, okay? And so we're going to have some initial velocity here. I'm going to draw in our initial velocity vector. And this is going to be at some angle theta naught, and it'll have some magnitude v naught, right? And so we've already talked about in the previous couple of videos how we can break up our initial velocity into its x and y components. So I'm just going to skip right to the sort of answer of that. So our v0x is going to be equal to v0 cos theta 0, and our v0y is going to be equal to v0 sine theta 0, right? So we're going to need to make use of these in building our range formula. Okay, so we're still dealing with a projectile, and as we talked about in the previous video, for a projectile, our acceleration in the x direction has to be equal to 0, and this means that our v0x is equal to vx is equal to some constant, right? Because there's no acceleration in the x direction, so the velocity in the x direction is always constant. And we saw that with these circumstances, all of our kinematic equations in the x direction reduce down basically to this, right? And so if we take our initial x coordinate, to be 0, and we take our final r, or our final x coordinate to be our range, right? Because our range is going to go from x naught to x final, and so that's going to basically be r. That's the range that we're looking at. If that's the case, then we can write, by substituting in r for our x value here and setting x naught to 0, we can write r is equal to excuse me, vxt, right? So this is great, and we can also make the substitution that we can substitute in for vx, because we know that vx is equal to v0x, and so we can simply substitute in our expression up here for the breaking up of our velocity, or our initial velocity vector, and we end up with r equals v naught cos theta times t. Okay? Now, the question is, what's t? We'd like to have an expression for t so that we can easily calculate the range of this projectile if all that we know is its initial velocity, so that's the magnitude of its initial velocity and its launch angle, and also require that the projectile lands at the same height as it was launched from. Right. This is our requirement for the range formula. That's always going to be a requirement to be able to apply the range formula. Okay, so how do we find t? We are going to exploit the symmetry of the problem to get to t. So notice that if we're ignoring air resistance, which we are for all projectiles, the symmetry of the problem means that we sort of have a line of symmetry here, right? It's going to be the same on one side as it is on the other of that line. It's basically a reflection of what's happening in the first half of the trajectory to the second half reversed, right? So let me make a note here. So due to symmetry, we can exploit this symmetry, and if we think about it, we can see that v0y, the y component of our initial velocity, is going to be equal to the negative of vy. Right? So let's take a look at that and think about that for a second. So the y component of our initial velocity over here, so we're going to have some initial upward velocity here, right? We're going to have some initial v0y, and if there's no air resistance and the problem is totally symmetric, we're going to have the exact same magnitude, but in the opposite direction for our vy over here. Okay, and because that's the case, we can exploit this fact, and we're going to see how we can use that. Because this is the case, we know from up here that we can write our v0y in this form, right? And if we just hit all three parts of this equation with a minus sign, this is going to give us the equation that I'm going to write down here. So vy equals minus v0 sine theta equals minus v0y, right? And so now we're going to use one of the equations that we derived or talked about. Well, we derived this back in our first module, and we talked about it last video. We're going to make use of this equation here. And if we now substitute in from our result up here for vy, we're going to get I forgot to put the zeros on the theta here. We're going to get the following expression here. Right. And we can now clean this up a little bit. So we're going to move the v0 sine theta on the right-hand side of the equation over to the left, and this is going to give us minus 2 v0 sine theta naught equals minus gt, and then dividing through by a minus g gives us t is equal to 2 v0 sine theta naught over g. Okay, and so let's put a little dotted box around this, and if we substitute equation 2 here into equation 1, I think we can see how we're going to end up with the following. And I'm going to drop the zeros on the theta now, so we just clean things up. I'm just going to call this theta naught theta, and we're going to end up with this equation here. Right, now I can rewrite this slightly to clean things up. Let's say we write it like this. right? Because we have two v naughts here, and so they're going to be it's going to be v naught squared. Can I erase this? No. Okay, over g, and then we have 2 cos theta sine theta. Now this may be familiar to you guys, but this expression in here, there's a trig identity that tells us that 2 times the cos of an angle times the sine of an angle is simply equal to sine of twice that angle. Okay, so that's a trig identity, and this allows us to rewrite this in the following form here. Okay, and this what we have here, this is what's known as our range formula. So we have to be very careful here. This is telling us what the range of a projectile launched with the magnitude v0 and a launch angle of theta, what that range is. So it tells us what r is if we're given v0 and theta. But it's only applicable in situations where our y0 and our final y are both equal to 0, right? Remember, we made this requirement up here, right? And so we have to be very careful. We only apply it where the launch height of whatever it is that we're launching is equal to the landing height. Anywhere else, and this won't apply. But so we end up with this sort of useful equation that we can make use of, and I'm going to do an example in a moment. But before I do that, I just want to point out one thing about the range formula. Maybe I'll skip the rest of this page and start down here. So note that I'm going to draw another set of coordinates here. Note that, or maybe I'll just rewrite here. I'm going to rewrite the equation also. Note that there's always, well, in almost all cases, there's 2 angles, 2 thetas for which we're going to get the same range, right? So we can imagine this. Imagine you have some sort of a cannon or something firing a cannonball, right? First, I guess the first question is what's the maximum range for our cannonball, given that our v0 is constant, right? So if we have a constant v0, what angle should we choose to get the maximum range out of our cannonball? Well, that's clearly going to be whatever angle it is that maximizes the value of this sine 2 theta. Well, sine of whatever angle is going to vary, and it's going to go somewhere between 0 and 1, right? So you can imagine you have your unit circle, and that's too small. But we can quickly imagine that we have a unit circle here. And some angle. For what angle do we get the maximum value out of sine? Well, sine is always just the measure of this angle across, or this side across from our angle. So we get the maximum value of sine theta for a theta equal to 90 degrees, right? And so what we want here, because we have twice that angle in our equation, is we want 45 degrees to get the maximum range, right? So imagine back to our plot here. Imagine we draw the trajectory of a cannonball, and it lands here. If this theta is theta max, then that theta must be 45 degrees, right? But for every other, and actually maybe I'm going to clean this up a little bit. So, so for every other angle other than 45 degrees, we can see sort of that that there's going to be two angles that give us the same value, and we can just see this by looking at the plot here. Imagine we launch a cannonball with some angle less than 45 degrees, so it lands something like this, right? Well, then there must be some other angle if we launched it at more than 45 degrees that it would take a trajectory that looks something like this, right? Up higher and land lower. And this is true for every landing position other than our maximum one. So if this is x max and this is xi, then there's always going to be two thetas that are going to give us this xi, right? So we can imagine again, let's say we do another one. We launch at a very low launch angle, so it kind of just flies forward and lands here. You can imagine that if you launched at a very, very steep angle, there would be another theta for which you would get a trajectory that looked something like this, right? And we could draw these all the way back down until we get to our origin, right? So this is not this part here is just sort of a thought exercise, just to realize that for whatever range we're talking about, there's going to be one launch angle that gives us the maximum range, and that's always going to be 45 degrees, given that we're ignoring air resistance and all the other stipulations that we put in place. But there's always going to be two launch angles that give us any other value other than x max. And so our first launch angle, let's say we call our first launch angle theta for whatever range we're looking at, then there's going to be a complementary theta c, which I'm going to call theta c or theta complementary, and this is always going to be equal to 90 degrees minus the original theta. And so I won't prove that here, but we can kind of think about it in the following way. So just very quickly, imagine we had the sign, and maybe I'll write it out fully. So imagine we had some range, and we know that we can write the range as our formula above shows. But let's say we had some range, and in this case we chose a launch angle of 15 degrees, let's say, right? So this stuff is not going to be changing, right, as we change the launch angle, but this stuff will change because our theta is changing, right? So if this first constant out front stays the same, then this is just going to end up giving us v naught squared for whatever v naught is over g sine of 30 degrees, right? And this sine of 30 degrees ends up giving us 0.5, and so we end up with v naught squared over g times 0.5. But by using this idea here, we can see there's going to be another angle that's going to give us the same value, and we can see that here. If we chose, well, what's 90 minus 15? Well, that's 75. So if we chose 75 degrees as our launch angle, we would end up with v naught squared over g sine of twice 75. Well, that's 150. And it just so happens that the sine of 150, well, that's also 0.5. And so we end up again with v naught squared over g times 0.5. These are the same. Okay, and all this just to demonstrate that if our launch angle is not 45 degrees, there are two launch angles at which we're going to get the same range. Okay? And so that's just sort of a short discussion on the range formula. We're now going to do an example in which we look at applying the range formula to a sort of actual problem here. Okay, so we have our archer example here. An archer fires an arrow at a target that's 75 meters away. The bullseye of the target is at the same height as the release height of the arrow. Okay, so before we actually get into any of the sort of problem solving, let's draw out what we have here. Okay, so our solution, start off with our coordinate system again. we have our arrow being launched from the origin, let's say, and it lands somewhere out here. This is, we can imagine that this is the sort of target, right, with a bullseye, and this is where the archer fired the arrow. Okay, my drawing's not great, but you can imagine, right? And so we're going to have some initial launch angle, we'll call that theta, and we're going to have some initial velocity with a magnitude of, well, in part A, it's given to us as 35 meters per second, okay? And this is x equals 75 meters. Obviously, this is x equals 0, right? Okay, so we need to find, well, in part A, if the arrow's initial speed is 35 meters per second, which we already put into our diagram, what angle must it be released at to hit the bullseye? That's the question we want to answer in part A. Okay, well, so one strong clue here that we might want to use the range formula is that the arrow is launched from the same height as it lands at, right? And so anytime we see a projectile problem where we have the same launch height and landing height, we want to think about the range formula. It doesn't mean necessarily that we have to use a range formula. There's always other ways to answer these problems, but the range formula can give us a significant sort of shortcut in how we can answer this problem. So let's start off by writing the range formula. And so by direct substitution here, we can kind of solve the problem. First of all, we want to solve for theta, right? And so let's isolate theta first. We're going to end up with, well, let's move the v0 squared over g over to the left side and kind of rearrange things. So we're going to end up with sine 2 theta is equal to, rg over v0 squared. Let's take the inverse sine of both sides. So we end up with 2 theta equals sine to the minus 1 rg v0 squared, and then divide both sides by 2. So we have theta equals 1/2 sine to the minus 1 rg v0 squared. Okay, and basically we're kind of done here, right? We know what r is, we know what g is, we have our initial v0, the magnitude of our initial velocity of the arrow, right? And so we can substitute in and get theta equals 1/2 sine to the minus 1 rg, and I should be putting in numbers. So our range is going to be 75, g is 9.8 over 35 squared. And if you substitute in numbers, I won't do the actual arithmetic here, but if you substitute in numbers in your calculator, you're going to find theta equals 18.43 degrees. Now, most calculators are going to give you this 18.43 degrees, but like we just talked about, we know there's another angle that could give us the same result here, right? Because we're not talking about an angle of 45 degrees. We know there's another angle that would correspond to this trajectory that I'm going to draw in here. And that should be a perfect parabola, but I didn't draw it that well. And we can easily get that. And this wouldn't be part of the sort of problem. This answer of 18.43 degrees, that would suffice as an answer to this problem. But just be aware that there is another answer that would look like this, basically 90 minus 18.43, so that ends up being 71.57 degrees. So that's just an extra angle that would give us the same result, right? If we launched at 18.43 degrees, we would hit the bullseye. Also, if we launched at 71.57 degrees, we would hit the bullseye. And again, this is ignoring all air resistance, right? Air resistance would certainly have some impact on the flight of the arrow. more so for the sort of high launch angle, but we won't really get into that here. We're ignoring air resistance. Okay, so in part B, what do we want to do? There's a tree halfway between the archer and the target with a branch at 3.5 meters above the release height of the arrow. Will the arrow pass over or under the branch? Okay, so we want to answer that question. So we now know theta, right? So let's assume we're dealing with a lower launch angle. When you're firing an arrow, you would normally be dealing with that anyway. But let's assume we're dealing with theta equals 18.43 degrees. We can now, from our breaking up of the initial velocity, we can find out what the initial velocity in the x direction was. So we know that v0x equals v0 cos theta, but this is just equal to 35 cos 18.43 degrees. And so if we do the calculation, we're going to find that v0x is equal to 33.2 meters per second, right? And we can do the same thing for v0y, right? v0y equals v0 sine theta. And if we do the same substitution, we're going to find that v0y is equal to 11.1 meters per second. Okay. And so now we need some additional information, right? So what else do we know about the arrow's flight? What can we use here? Well, one thing that we can use is the sort of symmetry of the problem, right? So if the tree is at the halfway point of the arrow's flight, well then we know at that point that the y component of our velocity will be 0, right? You can think about what's happening to this arrow. It's slowly traveling upward. At the very midpoint, it's going to have no upward. The magnitude of its velocity in the y direction is going to be 0, so it's going to have no upward or downward velocity, right? Because it's just going to be hitting the apex, the very top of its arc, and then it's going to start coming down. So at the point where the tree is, we know that our velocity in the y direction, so vy, is going to be 0 at the tree, right? So we can use that fact. If we know what v0y is and what vy is, we can use those two facts with this equation, the equation that we've talked about a few times now, and I'll write it here. To solve for where that arrow is going to be, right? So this is just one of the equations that we had generated in our first module, and we've seen it again here in our 2D kinematics module. But we know what Vy is, we know what V0y is, we know what Y naught is, we know what G is. So we can solve for Y, and Y is going to be the position in the Y direction of the arrow as it passes the midpoint of its flight, as it's passing the tree. So if we do that, let me scroll down a little bit. If we do that, well, I'll just start substituting in numbers, right? And so we know that what we just talked about, how Vy is going to be 0, so this is going to be 0 squared is equal to V0y squared, which is going to be 11.1 squared, minus 2, and G is just 9.8. Y is here, and our Y naught is just 0. And at this point, it's just a simple matter of isolating Y. So I won't do all the algebra here, but basically what we end up finding is that after we shift everything around, Y is going to be equal to 6.29 meters. And so we're told that the branch of the tree is at 3.5 meters. So even if we choose our low launch angle, our theta of 18.43 degrees, the arrow is going to pass over the branch. So the answer here is the arrow goes over over the branch, right? And this would also be true if we selected our higher launch angle, right? And so that would sort of constitute an answer to this problem.